So today we're remaking an oldie but a goodie, which was taking an object and sending it to its UV map. I got an email basically asking me, can you do this while preserving surface area? Which I thought was a interesting question, and it got me thinking the original method I used to make it was vector displacement. Nowadays we have geometry nodes, so let's just do it with geonodes. Let me just show you how to do it. So let's start off with an object that looks a bit more interesting. Again, everything I'm about to show you generally works with any object, but Suzanne looks more interesting. So with Suzanne, let's make that a geonodes, and our goal is to get this to look like the UV map. What does the UV map look like? This flattened out thing, or whatever you want to do with it, okay? How do we do that? Well, what I want to do is I want to recast the position, so I want to move stuff around, so I'm going to set position to what position? The UV map. How do we get the UV map? Well, let's bring this in here, which creates an attribute. So I want to say use some kind of data to remap this. The data it should be is we can actually import in the UV map directly. And you can see, oh, there it is. It looks a bit messed up. But if you just add a split edges, it makes it work. Basically, the thing about this is you have separate islands that can't be separate if there's connected geometry, and those islands correspond to this. Now, by the way, this should update with our UV map, which is a cool little thing. As you can see, it's updating down there. You can make pieces bigger, smaller, whatever. Okay? To generalize this a bit more, what I can do is I can take this, I take it, I mix it with the original position, so as if nothing changes, and now we have a slider that lets us go from one to the other. Okay? Now, the interesting thing about this is already, first of all, I've achieved what I did with vector displacement so much faster. So simple node group. But what's interesting about this is you're going to see the surface area, the amount of skin or the amount of face area total that's taking this up is going down, right? And you could correct for this by increasing it, but how do we do it mathematically with any shape, whatever? And this is what I was trying to answer. So here is what I came up with. To calculate the surface area that we need, what we need to do is we need to calculate the original surface area, this one. We need to calculate the final one and kind of get the difference and use that difference to then scale it up, right? So for example, I actually have an add-on that does this, the 3D print add-on. You can see right now this has a surface area of around 12.4 square meters. And now it has a surface area of a lot less, 0.6, which makes sense. It's significantly smaller. So we somehow need to extract these two numbers. Here's how I'm going to do it. So I'm going to add in a value node over here just so we can externalize this. And I'm going to take all this and make it into a node group. So again, I pulled out this value node so that we could control it from here. So think about it like this node group. What it does is it's the transition group. I want two of these. I want one of them in its monkey state and one of them in its flattened monkey state, which will not work until I plug stuff in. So we need this here, there we go. So monkey, not monkey. We need to calculate the surface area of each. To do that, we actually have a attribute or a field that was added kind of recently, face area. What it does is it gives you the area of every single face, and we somehow need to add these, okay? To do that, I'm going to use an attribute statistic. I want the statistics for our monkey. Give me the statistics about the face area. Specifically, make sure you set this to face. If you don't do this, it's going to come out a bit incorrect. Okay? So we're looking at the monkey, we're looking at its face area, and we care about the sum, the total. And we're going to divide that by something else. Okay? And now let's do that for the other one. So I also want to know the total face area. So again, for this geometry, the flattened version, I want to know the face area for face. And give me the sum, and then we take these numbers and we divide them. So just to be clear, this is the ratio that we need to account for with scaling. So this needs to be bigger by how much? By this ratio, or maybe the inverted ratio. I don't know. So let's try it out. I'm going to make another one of these with the geometry, with the UV map. Let's view it. So it goes from one to the other. I want to scale this so that it's the correct size. So we're going to transform by a certain size, and again, the question is, what is that size? Hopefully, it's this ratio number. So let's plug that in. And whoa, it's getting bigger, which is good, but it's getting too big. Why? Well, what we've done is we've calculated the ratio of surface areas. So it's saying one is 1.4 times bigger than the other or something, right? The issue is it kind of overextends, and we'll talk about why that is. But you can see now the area is huge instead of 0.6. And when it's like this, it's going to be even bigger. So the reason this is overextending is we have a transformation factor, but we are scaling not like as one like line, we're scaling on the X and Y axis. What do I mean? When we transform and grow this, we're scaling both in the X and the Y direction. So it's almost like whatever factor we have is being calculated twice. In other words, what I'm saying is take it and don't divide it by 2, but take a square root. Take a square root. And this should solve it because this will account for 2 axes. If this was a 3-dimensional problem, you take a cubic root. Okay? Now, the only issue is this is going to apply to both of these. So the scaling factor before, after, is also going to apply to our monkey. So I want to make sure that we also have a slider for this so that it only affects it some of the time. So I'm just going to outsource this right here, and let's see. There we go. So now when this is set to monkey mode, it's going to be multiplying or scaling by white, which is 1, and then otherwise. And it almost looks correct, but let's test it. So when it's in monkey mode, we have an area of 12.4, like we saw. And now, in this form, we have an area of 12.3. It's not the same, but it's very close. What do I attribute the difference to? Maybe square root rounding errors, but you can tell that this is essentially the same thing. And it works with absolutely any mesh. Let's try it. So instead of this mesh, we need something with a UV map. So let's try a torus. I'm going to make a geometry nodes group, use our old group. Where did it go? Oh yeah, we need to make sure it's using our UV map. And the reason that it's a square, by the way, is if you look at the torus UV map, is it's a flattened out rectangle, right? And we could alter that. But what this should now be doing is it's doing the transformation. Let's visualize it. So it's unwrapping our torus, but it's preserving the surface area. Let's see if it does. Area of the torus is 9.7 something. Area of the plane is 9.7. This one's actually much more accurate, as it seems. So that is how you preserve area. You're welcome. And this should work with any kind of UV map because of the math. So if I was to take this and do some kind of pinching, so I'm going to scale it down. So now our UV map looks like this. Let's make it even more extreme. Makes it a bow tie. We transformed from one to the other, but it's still going to preserve our area, as you can see, because it's going to do that calculation. So either way, highly specific node group for a highly specific question, but I wanted to remake an old tutorial in the context of geometry nodes and talk about this idea of conserving, whether it be surface area, volume, whatever. Volume would be tricky. Actually, no, it wouldn't be. Either way, thank you guys for watching, and let's wrap up this 9-minute tutorial. Okay, so at the end of these, I feel weird. I feel like I already ended it in my brain, but I'm still going. At the end of these, I always talk about Patreon, but wait, don't leave. There's a reason for you to click that link in the description. Listen up. There are 3 benefits you get when you join Patreon other than supporting these tutorials. First of all, you get early access to videos. I record these significantly in advance nowadays, so you could have seen this video multiple days early, and most uploads multiple days early, which is cool. You could comment before other people. You could see the tutorials, use them before other people, even, before it even comes out. The second perk, which is the main perk, is you get the blend files and the project files. So in the case of this one, I'm going to make this node group available, the surface area preserving thing, and you can just use that. But I've been doing this since 2019, so there's hundreds of blend files. And then thirdly, there's exclusive tutorials. I actually recorded one yesterday about putting text on any curve and doing animations and stuff with it. So I make those occasionally. What I try to do is I try to make most of the tutorials, like 99% of them, available for free on YouTube so you guys can watch. And if you want to donate and keep that running, that and the CG Matter channel, Patreon is the best place to do that. But there's a burp there. There's also perks. So whatever your reasoning is, I appreciate it. And I appreciate all 750 active patrons that you've been seeing. And hello to the newest patron, whoever that may be. Okay, thank you for watching, and you're welcome, emailer.